Hey, thanks for having a look. This video is based on some notes that I had prepared for a presentation to the Formal Aspects of Computing Science Specialist Group of the British Computer Society. Unfortunately, that meeting had to be cancelled, so I'm posting this here instead. And given the target audience, the emphasis will be on formal methods. And when I say formal methods, I'm talking about understanding something in terms of precisely defined mathematical concepts, as opposed to vague, intuitive concepts. Intuition is important, but it gets you only so far. When things get really complicated, it's best to have more of a formal theoretical framework to fall back on, so that, for example, you can check the correctness of something with a program, or verify it with a mathematical proof. That certainly turned out to be true in some work that I did on delay in sensitive circuits, about which I'll be saying more shortly. However, I understand that not many people are working in that area, so I'm going to try to keep the talk generic. My hope is that if you find anything to like in my approach, then maybe you'll be able to apply something similar in your own research work, even if it's in a different subject area. And if, regrettably, you don't like what I've done, then you can think of how you would do things differently and learn from my mistakes. So the way we'll organize this is I'll start with just a bare minimum of background about the subject of delay in sensitive circuits and develop it in an intuitive way, and then see about how we can make things more precise. So, to get started, I don't want to get too bogged down with this, but I do have to set the stage a little bit. So here's what you need to know about delay in sensitive circuits for now. They have no clocks. Does your computer run at 4 gigahertz? If it were delay insensitive, that would be a meaningless question. It would run as fast as it runs. Because they have no clocks, different parts of a circuit have to coordinate with each other by sending a signal that says, "Are you ready? I'm ready. Good, then we're both ready." That exchange is known as a handshake. Whatever you've learned in school about digital circuit design is useless for delay insensitive circuits. I'm talking about Boolean algebra, truth tables, maybe you've heard of Carnot maps, even logic gates. Delay insensitive circuits laugh at all that. Consequently, people don't like them. They're feared, reviled, ignored, misunderstood, distrusted. Nobody knows about them. Nobody wants to know about them. And if you've heard anything about Intel or Philips using unclocked circuits, never mind about that. It's none of your business anyway. So, on the positive side though, that means anybody who feels like it is free to develop this whole subject from first principles, doing everything exactly the way it should be done. How often, as a theoretician, do you get a chance to do something like that? So just to expand briefly on this idea of handshaking, suppose these two circuits, whatever they are, need to coordinate with each other. The one on the left sends a signal to the one on the right, and the one on the right answers with an acknowledgement back to the one on the left. If these two signals have been communicated by raising the level of a wire from low to high, then at this point both wires are high. But then if these two circuits ever want to do another handshake, they can't raise them again because they're already raised. So some would advocate a protocol whereby at this point the one on the left lowers the request line and the one on the right lowers the acknowledgement line. Then altogether 4 events have to happen for this handshake to complete, and it's called a 4-phase handshake. On the other hand, are these last 2 phases really necessary? Why couldn't you just have a protocol whereby we raise the wires the first time there's a handshake, and then we just leave them that way, and then the next time they want to do a handshake, they lower both of the lines, and then the time after that they raise them again, and so on. That way only two things have to happen for a handshake, and it's called a two-phase protocol. And that's great because it saves time, it saves energy, it saves bandwidth. What's not to like? Well, some people would say that two-phase circuitry is too complicated. It's too much of a pain in the neck to design it, or it's too costly, so it's worth using those extra phases just to cut costs. And who's right? I don't know. That in itself isn't a problem. The problem comes in when two circuits following different protocols need to interface with each other. And then what? Well, that's where this circuit comes in. A four-phase to two-phase handshaking protocol converter. So let's see a quick walkthrough of how this works. And this is all going somewhere. I used this same example in a presentation once, and it led to an awkward question from a very attentive member of the audience. So let's see if that happens again. Okay, so the thing on the left wants to initiate a four-phase handshake. It starts by raising this terminal labeled R4, which causes this wire to go high. And I'll highlight it like this whenever a wire goes high so that it's easier to remember. The signal from this wire reaches this device known as a toggle. A toggle has one input terminal and two output terminals. Whenever the level of the input terminal changes, either from low to high or high to low, the toggle changes the level on the dotted output terminal, and it leaves it that way until the next time the input terminal changes, and then it changes the level of the other output terminal to the opposite of whatever it is. And then it leaves it like that, and then the next time the input changes, it changes the dotted output again, and so on. So this signal from the dotted output on the toggle leads to this fork component, which broadcasts a signal to both of these two places. One of them is the request output on the two-phase port, and the other is to this device known as a join. A join has two inputs, one output. Whenever both inputs to the join change, the output changes in either direction to the opposite of whatever it is. So now on the two-phase side, it will acknowledge by raising this A2 input terminal, which causes this line to go high. So the join now has two inputs that are high. They've changed from low to high, so the join changes its output to high. The signal on that wire reaches this device known as a merge. A merge has two inputs and one output. Whenever either input on the merge changes, the output changes. So now the output from the merge goes high. As far as the four-phase side is concerned, the handshake is half done. So now it continues by lowering the R4 line. That makes that line go low. The toggle changes its other output, which makes that one go high. This input to the merge then makes the merge lower its output. So now, as far as the four-phase side is concerned, the handshake is all done. But some of these wires on the inside now have changed to a high level and stayed that way. So what happens the next time around when we have to do another handshake? Well, suppose the R4 line is raised again. That line goes high, leading to the toggle. The toggle this time lowers the dotted output, which sends a signal to the fork telling it to lower both of its outputs. The R2 output on the two-phase port goes low, so the two-phase side acknowledges by lowering A2. Now both signals to the join have been lowered. The join lowers its output. The merge therefore raises its output, and the four-phase side is half done. So it continues by lowering the R4 line. This signal reaches the toggle, which responds by lowering its other output. That lowered output line reaches the merge, which makes it lower its output. And then everything is back to normal. Everybody's happy. So here's the awkward question I told you about, if you haven't guessed already. Why do you really need this fork and join component in here? Wouldn't it work just as well if you left them out, like this? And that question boils down to the question of deciding whether two circuits are equivalent. How would you even define equivalence between circuits? One way of defining it would be if you put both circuits in black boxes and you can change the inputs any way you want, could you observe any differences on the outputs? And if you could, then they're not equivalent, but if you can't, then they are. And if you define equivalence that way, then obviously these circuits aren't equivalent, because if you raise the input A2 on this circuit, the change comes straight out on A4, whereas on the other version, if you raise A2, it goes no further than the join, and nothing ever happens on the output. So you could tell them apart that way. On the other hand, this could never happen in practice, because you're not supposed to raise the input A2 until after the output R2 has been raised, because that's what the two-phase protocol requires. So if you restrict attention to the environment in which these two circuits would actually be used, then they are equivalent. And if you follow through with this idea of equivalence with respect to an environment, the whole theory works out beautifully. But let's not go there at the moment, because we have a more pressing problem right now. How would we say anything sensible at all about the behavior of a circuit besides some hand-waving walkthrough? Ideally, we would like a semantic model that describes each component individually and then tells us what happens when we put them together. So how to proceed? Well, if you're a theoretician, this is the fun part. You get to make something up. How about having a Petri net model for each component with an open transition for each input or output terminal on the component that fires whenever that terminal changes its level, and the rest of the Petri net describes whatever happens on the inside. So, for example, we could model a toggle with a Petri net like this, and the idea is that when the input terminal changes its level, this transition fires, which marks that place next to it, which enables this transition on the top to fire, which marks those two places, which makes this top output fire as the next observable thing that happens. And along with that, the circulating token has changed to the other position. So then the next time the input fires, these two places that are marked enable this transition on the bottom to fire, which marks those two places and fires the other output transition, also making the circulating token go back where it started so that the cycle can repeat. Looks good so far. What about the model for a merge? Well, that's a lot simpler. We just need a transition like this that fires and marks that place in the middle, which makes the output fire. Or if the other transition fires, that place also gets marked and makes the output fire. For a fork, we need an input transition that fires and marks both of those places, which makes both outputs fire. And for a join, two input transitions. If they both fire, then both places are marked, which makes the output fire. Now what about putting them together? This calls for another idea. Suppose we label some of these open input and output transitions with labels like T0, T1, T2, and T3, and then follow a convention whereby two terminals having the same label and different components are really the same transition. So these two T0 transitions fuse into one like that. The same with T1, T2, and T3. Now instead of 4 Petri nets, we have just one. And does this Petri net have anything to do with the handshake converter circuit? We could label the remaining open transitions with the same labels that the terminals had in that circuit. And then if a 4-phase handshake is initiated, R4 fires, marking the place next to it. Those two places enable the transition above to fire, which marks the two places next to that. Another transition fires, 2 more places are marked, and R2 fires, the request terminal on the 2-phase port. Along with that, a transition fires internally, marking the place below it. When the 2-phase port acknowledges, it fires A2, marking the place next to that. Another transition is enabled, the place next to A4 is marked, and then A4 fires and the 4-phase handshake is half done. So R4 fires again, the place next to it is marked. These two places now enable the transition below to fire, which puts a token in the place next to it and also restores the circulating token. The transition below that is enabled and fires, marking the place next to A4. A4 fires and the handshake is complete. So in its own way, this Petri net is doing what the circuit is doing. Maybe this trick would work with any circuit. If we had Petri net models for the components, and we put those Petri net models together the same way those components are put together in the circuit, the Petri net that we get might tell us something about how the circuit behaves. Maybe there's a bug in the circuit and the Petri net would tell us that too, which would be great. So, does this idea have legs? Is it time to start writing something down instead of just drawing pretty pictures? This calls for the formal approach. This approach can be inspired by the intuition we've developed up until this point. Nothing wrong with that, but it will have to be a lot more precise so that there's no chance of ambiguity when it comes to settling hard questions about correctness. To make it a little bit easier, we can split it up into 3 aspects that can be understood more or less individually. That is, the matter of how things are connected in a network, the way components behave individually, and how this individual behavior manifests itself collectively when they are connected in a network. So first, the matter of network connections. Since we're temporarily ignoring the component semantics, it might just as well be a network of boxes connected by arrows, and we're looking for a formalism that captures all of the information about a diagram like this, so that we can proceed with further analysis without reference to the diagram. Maybe this description would take the form of an algebraic expression. Another nice feature for it to have would be if it were hierarchical, in the sense that it allows large boxes to be expressed as some combination of smaller ones and suppresses the details of the way the smaller boxes are connected on the inside of the large one. Where to go from here? Well, again, we'll have to make something up. We wanted an algebraic description, so how about an algebraic structure called a blockoid? I made up this name blockoid as a joke, but I can't think of a serious name that fits, so blockoids it is. A blockoid over a set B is an algebraic structure consisting of a distinguished element I in B, a unary operator Z mapping B into B, and a binary operator rack mapping a pair of elements of B into an element of B. And these must satisfy the blockoid axioms, about which I'll be saying more in a moment, but not before developing some intuition about them. When we think of a member of the set B of blocks in a blockoid, we should picture it as a box with some fixed number of inputs and outputs, shown here with the inputs on the left and the outputs on the right. And these inputs and outputs are well ordered, so it's meaningful to talk about the first input, the second input, and so on. Same with the outputs. We might draw a block like this, or if we don't want to be specific about the number of inputs and outputs, then like this. And we should picture the set B as the universe of all such blocks. Now, as for the operators, we should think of the operation Z as that of connecting the first output on a block to its last input. The rack operator puts 2 things together without connecting anything to anything else, but the order matters. The first inputs on the result correspond to those of the left operand X, and the rest of the input to those of Y, the right operand. Same with the outputs. And the block I has just one input, one output, and nothing between them but a connection. So let's see some examples of these operators, which will turn out to be useful in a moment. Take a block X, form the expression rack IX, Z rack IX, and now we have a block that looks just like X from the outside, except that the inputs have been rolled down one position. Or take another block X, form the expression rack XI, Z rack XI, That gives us a block that looks just like X from the outside, except that the outputs have been rolled up by one position. We can apply these operations any number of times and therefore roll the inputs or the outputs any number of times. That means without being told, we could infer the number of inputs or the number of outputs on a block just by counting how many times we need to roll it until we get something like the original block back again. But that all depends on a concept of equivalence among blocks. So let's make it a requirement. To have a blockoid over a set B, B must admit an equivalence among its members, which is also a congruence. And by that I mean if X and Y are equivalent to each other, then ZX must also be equivalent to ZY, and similarly for RAC. And some of you will say, yes, but how is this equivalence defined? From a formal point of view, I don't have to tell you. That's how theoreticians roll. If you're proposing a model for this theory, then you tell me. And whatever you tell me, make sure it meets these conditions, or else you don't have a blockoid. So anyway, given a block X, we can define the input arity and the output arity of X, meaning the number of inputs on X and the number of outputs on X, as the minimum numbers I and O, whose existence is asserted by these conditions. And for convenience, we can denote the input arity of X as capital I of X and the output arity as capital O of X. Doing that gives us everything we need to capture all of the intuition about blockoids illustrated in those diagrams in terms of this short list of simple axioms, each of which has a clear interpretation. For example, applying Z to a block X gives you a block with one less input and one less output exposed to the environment. If you like proving things, you could prove that the block I has exactly one input and one output. That condition is a consequence of the axioms without having to be an axiom of its own. Furthermore, and this is something you should strive for whenever you make up a theory, the axioms don't overconstrain the models for the theory. They specify only what is important and leave the rest. There could be more than one model for this theory, as long as they all satisfy the axioms. We'll see in a little while that it's very helpful to have that flexibility. But first, let's see if we can use these operators to specify a real network. Suppose we have a blockoid and these are the blocks. We can start by putting the toggle and the fork together in one block and the join and the merge together in another block using the rack operator. Now if we want to connect the toggle to the fork, and if we want to connect the join to the merge, we can do that using the Z operator in both cases. Now we can put both of these together using rack again, and we can connect the toggle to the merge using the Z operator. And finally, we can connect the fork to the join using the Z operator again. So we get a circuit like this that can be specified as shown. And if you twist your head around enough, you should be able to convince yourself that you've seen this circuit before. Which is good. But are these operators general enough to cover any circuit that might ever come up in practice? I'm going to claim that they are. Here's why. Suppose you have some collection of blocks. They can be any blocks at all. Suppose you want them connected in some way that might be very complicated. Even then, you can accomplish that with a circuit like this. That is, feed the outputs from the blocks B0 through Bn into some permutation network P, and then take the outputs from the permutation network P and feed them into the inputs on the blocks. For a suitable choice of permutation network, you can arrange for anything to be connected to anything else. And it turns out that you can express this circuit in terms of block operators by taking a list B of the blocks in any arbitrary order, concatenating that list with the unit list of the permutation network P, and then folding the rack operator over that whole list. Here I'm using some notation for the functional programming operators of fold and concatenate. Then you have 3 more terms necessary to express the buses shown in the figure. The bus widths are given by the summations of the arities of the blocks. This operator T, as we've seen before, is that of putting a wire in parallel with a block. And the S operator, defined as Z composed with T, is that of rolling the inputs on a block by one. So the missing piece here is the permutation network. However, if we could show that any permutation network is expressible in terms of the operators rack, Z, and I, then it would follow that any network at all is expressible in terms of those operators. For that, we're looking for an operator P that takes a permutation X to the corresponding permutation network P of X, where P is defined in terms of the blockoid operators rack, Z, and I. We can assume a convention whereby the permutation X lists the output terminal numbers in order of the inputs connected to them. So for example, if X starts out with 9, 6, 2, and so on, that means the first input is connected to output number 9, the next to 6, the next to 2, and so on. So poking around for a solution, we could roll X to the left by 1. Now we have a different permutation and a different permutation network. So what? We could roll it again. Now we have yet another permutation and another permutation network. Who cares? If we roll it one more time, however, something interesting happens. We have a permutation network expressible as a wire in parallel with a smaller permutation network. And this smaller permutation network is given by a permutation X prime obtained from X by rolling it to the left H times, dropping the first term, and then pointwise decrementing the rest of it. Here I'm using some notation for rolling, dropping, and decrementing, where H is the index of 0 in the original permutation X. And this result is expressible as rack of I with P of X prime. But if we define the operator T as that of putting a wire in parallel with something, it reduces to T P of X prime. But this is still not the permutation network for the original permutation X that we're given. However, if we roll it using the operator S defined as Z composed with T, roll it again, keep rolling it until we rolled it H times, then we do get back to the original permutation network that we're looking for and that corresponds to the permutation X. This observation suggests that P could be defined as a recurrence, where the base case is a permutation network of just one wire, and the inductive case amounts to taking the argument X, rolling it until it starts with 0, finding the permutation network recursively for the rest of it, putting a wire in parallel with that result, and then rolling it back where it started. So that's a pretty good indication that these operators rack, Z, and I are universal for all block diagrams. And it's nice to know that this algorithm for generating permutation networks is not computationally expensive in case we ever want to use it. It handles whatever you throw at it. And we have, at last, something to check off our list, the matter of describing how anything can be connected into a network. Next up, we'll have to take a look at delay-insensitive component semantics. We saw previously that open Petri nets could be useful as component models. So to follow through with that idea, we'll represent a Petri net as one of these tuples consisting of a set P of places, T of transitions, and so on. That's pretty standard. Some might also like to include a subset F of the places representing the final marking. No harm in throwing that in as well. And then we'll say that every component in a circuit is one of these tuples representing a Petri net. The only problem with that idea is that it doesn't quite tell us everything we need to know, because we don't know which transitions in the Petri net are the inputs on the component and which ones are the outputs. So maybe we can improve on that a little bit by having this universe D of Petri net modeled delay insensitive processes, where each element of D consists not only of a Petri net N, but an explicitly noted input alphabet and output alphabet, which I'm denoting I and O here, but that has nothing to do with the previous usage of the letters I and O. They're just dummy variables. We don't have enough letters. Blame the Romans. And then the question is, does this model of a component enable the concept of equivalence as required if we want to define a blockoid over this set? And the equivalence we're looking for here is sort of a behavioral or observational or black box or extensional equivalence, whatever you want to call it. The idea is that two Petri nets that are constructed differently might nevertheless be equivalent if their observable transitions both fire in the same order. And the answer to that question is yes, but it's a little bit complicated. I need to gloss over some things here, enough to fill 3 or 4 chapters in a book, but I'll give a reference to it at the end. And anyway, it's pretty standard stuff. If you know anything about Petri nets, you know that you can build a reachability graph whose vertices are the markings of the Petri net. From that you can infer a finite automaton recognizing the quiescent traces of the process that the Petri net represents. A quiescent trace is a sequence of transitions obtained by traversing the reachability graph starting from the initial marking up to a marking where there are no transitions enabled except possibly for input transitions. Along with that, you can also infer a finite automaton recognizing the divergences of the process. A divergence is a sequence of transitions having a prefix that is obtained by traversing some path from the initial marking in the reachability graph up to a marking where an enabled transition has a marked place in its post set. From these two automata, you construct an automaton recognizing the union of their languages, which I'll call the relational trace set. And the relational trace set induces a concept of refinement by containment. That is, a process X is refined by a process Y if the relational trace set of X contains that of Y. The refinement relation among processes is a complete partial ordering, so that we can picture it as a diagram like this. Each dot in the diagram represents a process. The one at the bottom is the most useless, good-for-nothing process. As we ascend up the diagram, we find more useful processes. The idea is that if one process is above another in the diagram, then the one above is always a compatible replacement for the one below in any environment. But if two processes are sideways from each other, then neither process is compatible with the other. A definition of equivalence follows trivially from refinement. If two processes refine each other, then they are equivalent. And since we can check for refinement mechanically, we can also check for equivalence mechanically. Given this concept of equivalence, we're now making some progress toward a workable semantic model for delay-insensitive circuit components, but we can still do better. A situation that's bound to come up in practice is that of having more than one of the same component in a circuit, such as more than one merge or more than one join in the same circuit. Intuitively, we know that these are the same kind of component, but they're not literally the same component, and we might distinguish among them by having them labeled differently. So I'm going to suggest that a more convenient semantic model would allow the components to be parameterized by these labels. To accomplish that, we can model each component by one of these triples, I, O, B, where I and O are the input and output arities, noted explicitly as numbers, and B is not a process, but a function that returns a process when you give it this pair of lists, small I and small o, of alphabet symbols. The process it returns has those symbols in its alphabets, and the order matters, so they have to be lists of alphabet symbols rather than sets. And so I'm using this notation for the range of a list, meaning the set of its terms. And when we do that, it's no problem to have a concept of refinement among primitive blocks induced by refinement among processes. All we have to do is instantiate two blocks as processes with the same alphabets, and then check those processes for refinement. And here I'm using this notation for list truncation. So it seems that we can check one more thing off our list now. We have a way of talking about how components behave individually. Now all we have to do is get around to describing what happens when we put them together into a network. A good way of doing that will be to define a blockoid over the universe B of primitive blocks. That way we can express any network we want as an expression in terms of block operators, and when we evaluate that expression, it will reduce down to a single block whose semantics is well understood. If we want to compare one network to another, all we have to do is express both networks using block operators, evaluate both of them down to a single block, and then compare those blocks for refinement. Since we've already had the foresight to ensure a concept of equivalence among primitive blocks, all we need for the rest of this construction is operators RACB, ZB, and IB that satisfy the blockoid axioms. For IB, we want a component that acts like a wire, so the input and output arity will both be 1. And the other thing we need in this triple is a function bi that takes a pair of unit lists of alphabet symbols and returns a process whose alphabets contain those symbols and whose petrinet looks like this. That is, it needs some arbitrary but fixed place p in the middle. It needs transitions determined by the argument to the function bi, and arcs and markings defined in the obvious way. RACB is a binary operator, so it takes two blocks. The arities of the resulting block are given easily enough as the sums of the arities of the given blocks. The function br associated with the resulting block takes its arguments little I and little o, and it feeds the first part of those arguments into the function b associated with the left operand to RACB, and it feeds the rest of those arguments into the function b prime associated with the right argument to RACB. Then it takes the processes returned by those two functions and combines them by parallel composition. I'll skip the formal definition of parallel composition of processes, but I'll give a reference to it at the end. It's pretty much what you would expect anyway, a disjoint union of their petrinet models and a few other conditions. Finally, we have the ZB operator. The arities of the resulting block are given by decrementing the arities of the operand. To evaluate this function bz associated with the result, we choose two arbitrary distinct unit lists p and q of alphabet symbols that differ from any of those in the operands I and O to the function bz. Then we form this specially constructed pair of lists and feed it to the function b associated with the operand to zb. Evaluating this function gives us a process whose petrinet model has a last input of q0 and a first output of p0. Along with that, we construct a petrinet model for a wire, as we've already seen how to do, with input p0 and output q0, and then we combine that using parallel composition to obtain a result that looks just like the operand to zb with its first output connected to its last input. And if these operators RACB, ZB, and IB satisfy the blockoid axioms, which they do, but I'm not going to prove it. We can check one last thing off our list. We've now given a formal account of how components behave in a network. So now what? Well, computer science is an applied science. Eventually it has to hit the ground and get real. This theory is no good unless it helps someone design a real circuit. And when you go to have a circuit fabricated, you'll be asked for a netlist. Not some fancy algebraic description, but a straight-up text file listing all of the components in the network, numbered in some unambiguous way to indicate exactly what's connected to what. So how do we get from this algebraic description to a netlist? Well, here's an idea. We'll use a high-level intermediate representation, call it a hierarchical block, and denote the universe of all hierarchical blocks by H. While we're at it, we'll denote the universe of all netlists by L, and then we'll have automated transformations, taking a hierarchical block either to a member of B if we want to know something about its semantics, or to a member of L if we want to ship it out to have it fabricated. And we'll make these transformations so simple and obvious that we can trust them. That way we'll have some reason to think that the block diagram has something to do with the netlist. And how is that going to work? The plan will be to define blockoids over H and L with structure-preserving maps between them. All we ask of our intermediate representation H is that it capture the form of a block expression. There are various ways that can be done, but one very simple one is to use nested lists of primitive blocks that can be nested to any depth. So any primitive block is already a member of H, and any list of members of H is also a member of H. Then we use the unit list of a block X to indicate the Z operator applied to X, and any list of more than one block to indicate the rack operator folded over that whole list. Given those interpretations, these definitions of rack, Z, and I follow more or less automatically. One way of thinking about the transformation THB from H to B is that it is whatever makes this diagram commute for the Z operator and this one for the rack operator. Another way of thinking about it is that it's like evaluating an expression by traversing its abstract syntax tree recursively. And here I'm using this notation for mapping a function over a list. In any case, once we have THB, we also have a concept of refinement over hierarchical blocks, induced by refinement over primitive blocks. That is, we convert two hierarchical blocks into primitive blocks and then test them for refinement that way. So that was the easy part. Now what about netlists? We'd like to have a way of building a netlist that corresponds as closely as possible to the block expression used originally to specify the circuit. So we can start by imagining the terminals on each component numbered consecutively from 0, and whenever there's a rack operator, the terminals on one of the components get their numbers bumped up so that they don't clash with the other one. So now we have the fork starting with 3 and the merge also starting with 3. Now when there's a Z operator, we identify the same number with terminals on two different components. So now the toggle and the fork both have a terminal numbered 3, and the merge and the join both have a terminal numbered 4. Then if we apply rack again, the terminals on the latter components start with 6. The Z operator now identifies 2 with 9, and another Z operator identifies 4 with 7. So the circuit diagram now has terminal numbers identified with all of its terminals. We don't even need to look at the circuit diagram anymore. We could just look at the circuit components and the numbers on their terminals to tell us what's connected to what. We can make a list of these where each term in the list consists of a list of input terminal numbers, a list of output terminal numbers, and the type of component that it is. And so our running example of a handshake converter reduces down to a netlist like this. That tells us how to define our universe L of netlists. Now, to enable automated transformation from our intermediate representation H to L, we need to make a blockoid out of L, which means we need to find definitions for operators RACL, ZL, and IL that do the same thing as we've just done informally with that diagram. IL is easy enough. It's just a unit list containing a triple with the block IB and the unit list 0 of input terminal numbers and the unit list 1 of output terminal numbers. ZL needs to be whatever makes this diagram commute, and RACL needs to make this diagram commute. And for the transformation THL, we're looking for a recurrence similar to the one that we saw for THB, with ZL and RACL remaining to be seen. The base case, however, corresponds to a primitive block H with input arity I and output arity O, and the result is a unit list containing a triple with the block H and a list of input terminal numbers and output terminal numbers whose lengths are determined by the arities of H. And here I'm using this iota notation for lists of consecutive natural numbers. To make the rest of this a little bit easier, we can temporarily write I of x for the set of all input terminal numbers appearing anywhere within a netlist x, and O of x for the set of all output terminals. We can combine these terms in various ways to express things like the first externally visible output or the last externally visible input. Then we can easily define ZL of a netlist x in terms of a rewrite rule applied to every input terminal number in X that rewrites that number to the first output if it just happens to be the last input, but otherwise leaves it the same as it is. We can also define RACL of a pair of netlists X and Y as X concatenated with a netlist derived from Y by offsetting every input or output terminal number appearing in Y with the successor of the maximum terminal number appearing anywhere in X. So that mostly covers the theory. Now what can we do with it? Well, we could use it to specify and verify large complicated circuits that would be too big to do by hand, such as, for example, a multi-way merge parameterized by the number of inputs n. We can express the whole family of multi-way merges in terms of a single recurrence. In the base case, a one-way merge is just a wire, and a merge with some large number of inputs is obtained by two multi-way merges, each having roughly half that number of inputs, combined by a single primitive merge. And some of you will say, is that it? Binary trees? Tell me something I don't know. All right, but it will take more of a setup. Here we have an intersection of two streets with a traffic light. For simplicity, let's say they're one-way streets. The streets also have pressure sensors on them, so that when a car comes along and rolls over one of the pressure sensors, the light facing that car turns green and allows it to pass through the intersection. If another car comes along on the other street and rolls over a pressure sensor while there's already a car in the intersection, the light facing that car doesn't turn green yet until the one that's in the intersection rolls out of it and rolls over the pressure sensor on the other side. At that point, the other light can turn green, allowing the other car to pass through the intersection. To do a proper job of implementing this traffic control system, you need a device called an arbiter, which I'll draw as this little pinched box. When a car rolls over a pressure sensor on the way into the intersection, that makes one of the inputs to this arbiter go high, which makes the arbiter raise the corresponding output, which makes the light turn green. Then when the car rolls over the other pressure sensor on the way out, that same input to the arbiter goes low, which makes the arbiter lower the corresponding output, which makes the light change back to red. The two other lines on the arbiter work the same way, and they correspond to the pressure sensors on the other street. But the arbiter does some kind of magic on the inside to guarantee that it will never raise both outputs at the same time. And why have I belabored this point to such an extent? Because you'll be amazed at how much trouble this little thing causes. For one thing, people don't know what it is. If you hear a network guy using the word arbiter, he's probably not referring to one of these. On top of that, it's impossible to make an arbiter out of logic gates. Some people find that hard to believe because we're taught in school that all digital circuits can be made from logic gates. Smart people who understand things about transistors can design an arbiter circuit, but then a critic might say, that arbiter circuit of yours is prone to a permanent state of indecision, also known as metastability, if it happens to receive two input requests at the same time. And someone else will say that argument depends on Newtonian physics, which is wrong. I'm no physicist, but what I can gather about the physics of the situation is that the closer together in time the input requests arrive, the longer it will take the arbiter to come to a decision. But even if the requests are perfectly simultaneous, the arbiter will come to a decision in some finite, albeit unbounded time, because it will be resolved by thermal noise. With high probability. Unless the temperature is absolute zero. But maybe we don't need to worry about that because simultaneous requests are a zero probability event. On the other hand, didn't Einstein say that simultaneity is relative? How does that fit in? And on and on. The way I look at it is, you have to decide whether you're an engineer or a physicist. If you're an engineer, then the perfect model is not the one that is most physically realistic, but the one that captures just enough information to let you make the engineering decision you're trying to make. Would that mean your model of an arbiter should entail its thermodynamic properties? Maybe not. Maybe all we need to know about an arbiter for our purposes is the order in which its terminals can change levels. So let's label the input terminals R0 and R1, the output terminals G0 and G1, and model the arbiter by a Petri net, because Petri nets are ideal for things like this. Suppose a request is made on the terminal labeled R1. Then the transition R1 fires, marking the place next to it. These two places enable the transition next to that to fire, which does so and marks the two other places along the top. One of them enables G1. G1 fires, indicating that the terminal labeled G1 has gone high. Now when the terminal R1 is lowered, the transition R1 fires again, marking the place next to it. These two places along the top enable the other transition to fire, which does so, putting a token back in the middle. Also one next to G1, which fires, indicating that the terminal G1 has gone low. It works the same way along the other terminals. If the terminal R0 is raised, then the transition R0 fires, marking the place next to it. These two places enable the transition next to that to fire, which marks the two other places along the bottom. One of them enables G0. G0 fires, indicating that the terminal G0 has gone high. Now when the terminal R0 is lowered, the transition R0 fires again. The place next to it is marked. These two places enable the other transition on the bottom. It fires, putting a token back in the middle, and one next to G0, which fires, indicating that the terminal G0 has gone low. Now here's the beauty of it. Suppose both requests happen at the same time, or close enough that we can't tell the difference. Both input transitions fire, both places next to those are marked, and both transitions next to those are enabled. But whichever one fires next instantly disables the other one by evacuating a token from the middle place. Suppose the one above fires. It marks these two places along the top. One of them enables G1. G1 fires, indicating that the terminal labeled G1 has gone high, and no further progress is possible with the other request. Nothing can happen until the terminal R1 is lowered. Suppose it happens now. The transition R1 fires, marking the place next to it, which enables this transition along the top to fire. It does so, putting a token back into the middle place and also putting one next to G1. G1 can fire, indicating that the terminal labeled G1 has gone low, and progress can now resume with the other request. So the other transition along the bottom now fires, marking these two places along the bottom, and the rest proceeds as before. That is, G0 fires, indicating that the terminal G0 has gone high, and now when R0 is lowered, the transition R0 fires, marking the place next to it. These two places enable the other transition to fire, which puts a token back into the middle place, also puts one next to G0, which fires, indicating that the terminal G0 has gone low. Like I said, you can't make an arbiter out of logic gates. You probably won't find one on an FPGA. You'll be lucky to find one in any standard component library. You'll probably just have to get some silicon guru to do a custom transistor layout. But the good news is, you'll only have to do that once. Once you have an arbiter with two inputs, you can use that to build arbiters with any number of inputs. And why would you ever want an arbiter with more than two inputs? Maybe lots of reasons. Maybe you have a game show where the presenter poses a question and whoever knows the answer presses a button. But if more than one person presses a button, the first person to press it locks out the others, and only that person gets to answer. For that application, you would need a four-way arbiter. And here's one way to build a multi-way arbiter. Not a very good way, but good enough for a more interesting example than the multi-way merge I showed you before. The hand-waving argument for why this works is that whatever request prevails among the lower four still has to compete with the top one in one of those four arbiters on the right. And if you don't believe that, you can construct the PetriNet model for this circuit and compare that to the PetriNet model of your idea of a five-way arbiter. The point is, if you have a four-way arbiter, you can do this to make a five-way arbiter, and you should be able to do the same thing to make that a six-way arbiter, and so on. So it seems like we should be able to write a recurrence to capture this whole infinite family of arbiters parameterized by the number of inputs. And how would you write a recurrence like that? Well, if your functional programming foo is intact, then maybe something like this. That is, the base case of an arbiter with just one input is a wire, and an arbiter with n+1 inputs is some combination of the n input arbiter f of n with this complicated function applied to the list iota 1 to n, where we use the operator s as we have before to express rolling down the inputs on a block by one. To unpack this a little bit more, we can define a function g corresponding to a sub-expression above for the special case of n equal to 4, and then we can express f of 5 in terms of a fold with vacuous case I of g applied to iota 1 to 4, which expands to that, and we can lose the fold by writing that, and we can even get rid of the exponent in z to the fourth by writing that. To get any further insight, we can try evaluating f of 5 manually, starting from the inside out. G of 4i is, by definition, this expression with h instantiated as 4 and t as I. S to the 0 is just the identity function. So maybe this whole thing reduces to just a primitive arbiter. Let's see. Starting with I equal to t equal to a wire. S to the 0 of t is still a wire. By definition of G, rack of arb with that looks like this, and then Z makes that connection, rack of I again puts another wire below it, and one more connection, looks like we have an arbiter, just a primitive arbiter with the outputs flipped and then flipped again. So that would be g of 4I, which will instantiate as t on the next iteration. S of t just flips the inputs. Rack of arb with S of t gives us those two arbiters, and Z of that makes another connection. Rack of that with I puts a wire on the bottom and one more connection. So it looks like we have g of 3, g of 4I equal to those two arbiters connected like that. We'll call that t on the next iteration. S squared of t moves the first input down to the bottom. Rack of arb with S squared of t looks like that. And a Z with that makes one connection there. Rack of that with I puts a wire on the bottom, and Z again puts another connection there. So for g of 2, g of 3, g of 4I, we have these three arbiters connected like that. Call that t the next time around. And S cubed of t moves the first input down to the bottom. Rack of arb with that looks like this. Another connection. Rack of I, one more connection. G of 1, G of 2, G of 3, G of 4I looks like these four arbiters connected like that. Or in other words, fold with vacuous case I of G applied to iota 1 to 4 looks like those four arbiters in that configuration. So we put that together with F of 4, and then Z to the fourth connects the outputs on F of 4 to the inputs on those four arbiters. Notice it does it in the reverse order because Z starts by connecting the first output to the last input. And then one more roll puts that input up there. And the reason for all these rolls is so that the inputs and outputs end up in a consistent order. So we have the first input leading to the first output, second, third, fourth, and fifth. So I hope this example has shed some light on the motivation for this work, to describe families of complicated delay-insensitive circuits in general terms, and to be able to generate checkable semantic models from those descriptions, as well as having some assurance that the circuit you actually fabricate has something to do with the semantic model, because the netlist is generated automatically as well. And it was at this point that I stopped making any more slides because I found out the meeting was off, which is just as well because the video is already over an hour. But it's not the end of the story. The subtitle of the talk is An Exercise in Formal Methods. The exercise comes in when you, the theoretician, are called upon to revise a theory because there is some important question that it doesn't answer. I mentioned in passing that this arbiter I showed you is not a very good way to design an arbiter. So what would be a better way? What would be better about it? And how do you quantify how much better it is? This theory as it stands is silent on those questions. Getting to the bottom of them raises some nice hard problems in graph theory and probability. Maybe a topic for a follow-up video if I ever get around to it. Or if you want, you could read about it in this first reference here, which is probably a more appropriate medium for reading about things of this nature than a talking head in a video. The second reference I've thrown in here is another project that has some overlap, especially in the way Petri nets are used. I'm not involved with this project at all. Its goals appear to be more ambitious. From what I can gather, they're looking for a unifying theory of concurrent distributed computation, whereas I'd be happy if I could just get a circuit to work. It's well worth checking out, especially if you like category theory. And the third reference is some light reading if you're bored at home. Well, maybe not that light because it's full of differential equations, even though it's written in the style of a popular biography. The central theme of the book is the culture clash between theoreticians in the late 19th century and people who styled themselves as practical men. A practical man might say something like, "Don't tell me about Maxwell's equations, I don't need to know about them because I happen to have a very reliable intuition about the workings of transatlantic telegraph cables, which is why you can totally trust me with the money to build one. And I think there might be a lesson in there. People in electrical engineering use Oliver Heaviside's ideas today all the time, sometimes without knowing who originated them and without referring to them as formal methods. So all of you formal methods people, hang in there, stay healthy, because in another century or two you're going to rule the world. That's it. Thanks for watching.